we classify it by ourselves using our human knowledge. Yeah. So then these things here, these features are going to be like the inputs going into this network. So here there are 5 features. So you'll have to have 5 inputs, and the neurons in between, they are quite there is no strict rule, you know. If you have many neurons, it can capture complexities in your input data. If you have too few neurons, then it cannot capture the complexity enough. But if you have too many neurons also, neural networks have this problem called overfitting. So that means it will capture this table very nicely. That means it will not have any error when predicting this anything coming from this table. But the moment you show something else slightly different from this, it will start giving some errors, because the model has overfit too much to this data that it has seen. So this is one of the problems we have with neural networks, and that's why it's very important to not have very complex structures also. Yeah, then the output will be this target value, high risk, low risk. Yeah, these two. Okay. Yeah. Okay. So let's move on. Okay. So it will be a bit complicated. If you feel like you're like missing something, you just stop me. I can explain it to you. Yeah, and I also actually plan to redo this presentation maybe another day also, because if you hear me second time, I think there's higher chance you can keep up more easily. Yeah. Okay, so here perceptron structure. So previously we saw these neurons, right? So actually we can go deep into this to find out what is a neuron actually, or a perceptron. Yeah. Yeah. So if you see this diagram here, representation of perceptron. So what this actually does is very simple. It just multiplies the weight value with the input value, sums it together. That means you multiply this, multiply this, multiply this, and you sum all of them. Yeah. Then it goes through some non-linearity, and then it comes as output of this neuron. Okay. So it is also shown in this picture here. Yeah. So actually, why does this happen? Like, why do we even do this? You know, it's because I will explain it later. I'll explain it here. But before that, let me scale it up. So this is for one neuron. So let's say we have a network now, like 1 2 3 neurons. Okay, and this is these are the inputs, and they are, each input is connected to every other neuron, every neuron. Yeah. Then so if you take one neuron, it's connected to all the inputs, and this will have a weight, and these weights will be written as a kind of a vector like this. Okay, so you can write it as a vector, and the same for this neuron also. You have four elements of this vector. Then for this neuron also, you have these 4 weights. Okay. Yeah. Then you have a single input. Then you do this matrix kind of multiplication. So you have a weight matrix, and then you have some inputs, input, and then you multiply it. Then if you see the first row, you will have output for the first neuron. Then if you see second row, you will have output for second neuron. And there's something called B here. It's called a bias. We don't have to worry about that for now. Let's just see that this is like to write in a succinct way. If you want to represent, this matrix multiplication of all the neurons and the input, you can write it in this kind of matrix form. Okay. Okay. So basically, why does this thing even happen? Why are we even taking some input and multiplying with some weights? Okay. Um, yeah. So if you see, right, you should think of this as some kind of a dot product. Okay. So so this is a vector, right, and this is also a vector. So vectors, you try to draw it in on the plane, for example. So this is a 4-dimensional vector. Just think of a 2-dimensional vector for now. Okay. So if two vectors are aligned, then this dot product will have a high value, right? If they are far apart, like even 90 degrees, then the dot product will be 0, right? So basically, uh, some weights of the neuron, of a certain neuron, is trying to check if this input is aligned with its weights. Okay. So basically, so this is what we say, like different neurons are actually learning different aspects of the input data. So different neurons will have different weights. So after we do the training, right, they will converge to some certain weights for each of these neurons. And if this input and these neuron, and if and let's say we have output neuron, a few output neurons, then these will be connected to those output neurons, and the output is determining the class, right? I said that different classes will have different output. So if they connect to a certain output, then that's how the link is formed from a certain input going to a certain output. So some certain neurons will trigger, and if those neurons connect all the way to certain class of output, then that input will correspond to that particular output. Okay. So that's why the weights are learned during training, and they will learn to for that particular class. So they will be activated. This dot product will be a large value if that data point is corresponding to that particular class. Okay. So yeah, so that's the idea behind this dot product. Then after that, if you see, there will be this non-linearity part, right? So basically, non-linearity, what this does is it goes through this sigmoid activation function. It's called activation function. So the input to this function will be some value from this x-axis, which can be anything. Because you do a dot product, you can get a large value or a small value or something like that. Then it will just get mapped to a y value here. Okay. So if you see this curve, right, it is a non-linear curve. So actually this activation function is trying to bring some type of non-linearity into this into the neural network. Okay. Yeah. So in problems like regression and all, where the function is changing like crazy, then you need to have this sort of non-linearity in order to like follow the function. So that's why they bring in this activation function, a non-linear activation function. And also, if you see, this function is going to map whatever x value you give, it is still going to get mapped between 0 and 1. Okay. It's not going to go beyond that or anything. Yeah. So that is also important, so that the output coming from the previous like the previous neuron to the next neuron is a small value. Okay. It's not like a very huge value or something. Okay. So that it gets squashed between 0 and 1. Okay. um, and one of the main reason is like we are working with computers. So computers always prefer like small values to work with. They can't, you cannot give 1,000, 20,000, 30,000, and then it tries to multiply 10 like very large values, then it's going to have some truncation error and all that, right? So that's why we do this kind of squashing to map whatever you have to something manageable, like say like 0 or 1, 0 and 1, yeah, between 0 and 1. Okay, so next, yeah, actually this is just what I was saying. Maybe I will just read it just so that we can go one more time. So different neurons learn different aspects from input data. uh, so that means different neurons will learn different aspects. So when I say aspects, what I mean is like, okay, how do we say, for example, in this problem that we saw, right, in this table that we have, actually we are trying to quantify risk, right? So so something that like we can have, or okay, not only risk, okay, we are trying to quantify risk, but risk can be divided into like what are the things that can cause risk, so those are like the aspects that lead up to risk. So those aspects will be like, for example, uh, we think one of the aspect, like having a high value for age, means the person is a more responsible person, right? So this is an aspect that my human experience has told me to keep in mind. So whenever I see high age, I will think, okay, this person is a responsible person. So this is an aspect. So you can, so the neural network will actually understand these aspects. It will learn these aspects from the data, and use that to make decisions. And make decision means to fire certain neurons. So uh, so if you see in this picture, I have circled some neurons with the same color. Okay, so let us say, right, there are three output neurons. So let's say instead of just high risk and low risk, let's say we have high risk, medium risk, and low risk. Okay, let's say. So so if you see this, there is a blue circle here, blue circle here, blue circle here, and a blue circle here. So that means these are the neurons that have learned this high risk aspects, of from the input data. So whenever this is high, if you trace back, this neuron will have a high value, this neuron will have high value, this neuron will also have a high value. Okay, so so these are the neurons that have learned the aspects for a high risk customer. So then similarly for green, if you see this neuron, if you see this neuron, so these are the neurons that learned the aspects for a medium risk customer. Yeah. So this is what I was trying to say earlier. So when this gets activated, these will also have high activation values. These will also be high values. Yeah. So there is a saying like this in AI community, that is, neurons that fire together wire together. So those that fired together have wirings. That means they are connected. Okay, all the way to the end here. So necessary that these neurons are connected all the way to the output neurons. Okay. So weights of the neurons amplify the input signal and connect the input signal through the neurons of the different layers all the way to the correct out to the correct neuron that correctly classifies the input signal. Okay, that's what I was saying. Okay, then output of a neural network is a prediction or classification. So this is the output, and here is where we do the prediction. It's a high risk or low, medium risk or low risk, something like that. Okay, the circles of same color indicate neurons that fire for a particular class. Okay. Okay. So now we can get even deeper, actually. So I mentioned the word training, for example, in the previous previously. So now so what is this training? So a neural network, only after you train a neural network it is useful to anybody. If not, it's no use. So basically, so if you want, I can actually show you some summary first, then it will be a bit easier to understand. um, okay, so let's go through this slide first, then it's easier to understand. So AI development process summary. So if you want to develop some AI code, then this is like the general steps of so first, data is like one of the most important things you need to have. Then you train using you will split the data into some training set and test set, and then you will use the training set data to do some training. And then there is also this validation step, which is which is a slightly detailed topic, but basically validation is just part of training only, but it is for tuning the neural network structure. Okay, yeah, but sometimes, okay, let's say I told you to have a certain structure, then you can just avoid this validation part, you don't need to do this. Yeah, then after we do training, the weights in the neural network would have been updated, and then we can go to testing. So during testing, you show something you have not shown during training. Okay, yeah. So let's quickly go through. So the data types can be of two types in general for a neural network: something called structured data and unstructured data. So structured data is like some tabular form, like the one the table I showed you. Then unstructured data is images, sound, or sentences. So actually, instead of sending features in as input, you can even just send images, and you can even send sound. Then the network is smart enough to like interpret these things, but those are bit complicated networks like convolutional neural networks and so on. Okay. Then so structured data often does not require feature extraction before training. Okay. So what is feature extraction? Feature extraction means something like the table I showed you. Um, in deep learning, actually you don't even need this step called feature extraction. You don't even have to like create such a table like that to distinguish age or yeah, like separately tell features, this is a feature, this is a feature. You don't have to even tell that. So that's why deep learning is used for things like images, sound, and sentences. Like yeah, so it can create features by itself. Okay. So then training data should be comprehensive, varied enough to capture the underlying data distribution. So this means that you have to show all the different instances in your training. Yeah, you cannot show some part of the data and some other part of data that um, that is also possible. That means in real life, during the neural network testing case or when it is in production, you can have certain type of data, but you have not shown anything similar to that during your training, then it will perform poorly. So you have to have some similarity. Okay. And I say varied because high variance in all the different scenarios of data that you can show. Okay. So training step, training data is quite an important data set. You cannot simply you know just take a small subset and then say you have trained. Yeah, then it will not work correctly. Okay, then removal of outliers and biases is necessary to have a loss surface that is continuous, differentiable with fewer local minima. Okay, this is slightly technical. I will explain this when we go back. But basically you need to remove outliers. Okay, you cannot have something that will, like, skew your data. You have to yeah, so something that will that may not happen so often, better not to have it. Then split the data into training set, testing set, such that both sets are mutually exclusive. So these sets cannot have anything in common. So that's why during testing, um, the neural network sees something that has not seen during training, so that we can check the generalization capability of a neural network. So the generalization capability means how well can you predict correctly even to data that I have not shown you during training. But remember, this is different from this thing that I just explained, right? Your data set has to be comprehensive. So I have not shown you this, but it's somewhat similar to the training set. So it is not like totally different. It cannot be totally different, but it's not the same. Okay, so there's some similarity but not same. Yeah. Okay, then what happens during training? So training is a iterative process. So what happens is you have to iteratively perform something called a forward pass, which is you pass all the inputs through the network, get some output. Then you compare that output with your expected output, that is the target. So you check whether your target and the computed output are matching. So from this you can compute something called a loss. Okay, so that so loss will tell how different your prediction and the ground truth, the target value is. Yeah. Then there is a step called back propagation. So okay, now I know, okay, my network is not good. It has got deviation from the from this target, and the predicted value is deviating from this target. So I want to do some correction for it, right? So then we use gradients to back propagate through the network and adjust the weights such that the next time we do a forward pass, the loss is less, or the predicted output is close to your target value. Okay. Yeah. Then compute loss until loss is close to 0. So this means that you want all your inputs to have correct output, right? Then only you can say your network is trained well and it can predict as good as the target. Yeah. Okay. Then maybe we can skip this validation step, is for choosing hyperparameters like structure of network, the number of neurons in each layer. Okay.
Sorry to interrupt. I just have a small question.
Yeah.
Yeah. So what is that loss there? Like what it means? Like,
okay. So
difference between expected and the actual outcome, something like that.
Yes. So
Okay.
yeah, so this we have this network, right? Yeah, so we have this network. So we send some input, and then we expect it to be a high risk output. Okay. But let's say the network actually gave you a medium risk. Okay. So that means they are different, right? The target is for that particular input, you're supposed to get this, but your network is giving a medium risk. Okay. So there is a deviation between the the expected output and predicted. So then we quantify that as a loss.
Okay. Yeah. And in order to decide that, human intervention is required.
The human intervention part is to generate the expected outputs. That's all.
That is exactly. Right?
Yeah.
So for expected,
I give some input. Actually, it is not like that. What he is telling you is you will send a set of parameters. That is, you will send a set of things to train. So when he is doing that, he is not getting expected output. So what
Okay.
you will do is you will tune again and you will do. That's what he is telling. So the
Okay.
tuning part will be coming more on validation. That's what he is skipping because it's very complicated. Maybe I can something like a big data so that we can understand better.
Okay.
Peterson, can you go to the table? Yeah.
Okay.
Can you go to the next slide? You show me.
Okay.
Yeah. This slide I try to fit it into my big data thinking. Huh?
Okay.
So you got some input values are given. When the input values are given, he is having some attributes to check. That is to find out how much risk is there. To find out the risk, he is trying to fit these inputs into the attributes. For example, is he a drinker? You try to find it out. So he's putting some inputs. Inputs are the values. For example, it is fossils data. Fossil data is given as input. Whether the fossil is drinker or not, we have to find it out through the attribute. Do you understand what I'm trying to tell you? Yeah. Peterson, am I correct? Am I going in the correct direction?
Yeah.
Yeah. So you got attributes. Once you meet the attribute, Peterson will give a weight to that. You know, each attribute you may have a very high or low also. That's why he's telling about the high or low things like that.
Okay.
So certain attributes are for high, certain attributes is for low, something like that. Some pattern is there. Let us not think a fixed one. Okay, he is not talking about rule based. I'm trying to connect it to rule based for our understanding. That's all.
Okay.
So you got some weightage is coming out of that, right? That weightage is you know the input, you know the attributes. You expect the weightage to come automatically when you start training, right? But it is not coming means there is something else you need to do.
Okay.
Okay. So that you need to tune. That's what I'm saying in a simple word, tune. But tune is not easy here. Okay. Because already giving input, trying to make it go to the output, no deviation at all, like you say, the one very difficult. That's why he is getting some series here. The Z value, sorry, sigma value, the sigma value is there, right? The summation. When you go to the summation, you try to make it go. This is for only particular neuron. Am I correct, Peterson?
Yeah, this is single neuron. Yeah.
Single neuron. So this neuron itself is not behaving properly. Then how is going to get the whole set? Do you understand? Suppose you have a 10 neuron, the complication is going to be more. The more number of attributes you increase, it's going to be more complex. So you see the next picture, a simple neuron diagram. So he's giving some input. He's expect to meet a particular layer. That's what he's giving in series. The series is there, right? So he's trying to take 4 values as one set. So that there are 3 sets. Am I correct, Peterson? The WWW.
Yes. So,
yes. So he got 3 sets of inputs is coming with a weight. Okay. Then trying to fit into the attributes which are XXX, right? Am I correct, Peterson?
Actually, the 3 sets of not inputs, 3 sets of neurons. That is the blue corresponds to the neuron. Yeah, green neuron.
Correct.
Yeah, and the weight is this connection that is going to each of the
So
inputs.
this already is weighted for the inputs, right? These are all the inputs which are converted already with the weights, correct?
Yes. After that, it will become an output in each of these neurons.
Yes.
Yeah.
So that you try to fit it with the X1, X2, X3, X4 for further process, correct?
So we do a matrix kind of.
Then you try to put some correction value or something like that as a B, correct?
No, B is not a correction. It is just adding to this. This. It's you can think of it as a weight also. It is like a.
Oh, okay. It's another weight.
Yeah, it's like.
So this is also another attribute you're going to pass, but only the after doing the weightage of previous one. Then you will continue to do the weightage. Then you get a series of things so that you can find out where it fits. Correct?
Yes.
This WX1 is going to give you the final weightage. Correct? Then after that you try to fit it into where it goes or what output it goes. Correct?
Yes.
Yes. So the whole thing need to go smoothly. It is assumed to go smoothly. If it is not going smoothly, as you say, deviation, then you need to rectify.
Yes. Yeah.